Welcome back. So, if you recall, we have finished up the compound semiconductor portion of the syllabus. In the last class, we had discussed about 3 nitride semiconductors, introduced the concepts of polarization, how the material is polar, gallium nitride and its alloys, and we can make these LEDs based on gallium nitride and indium gallium nitride sort of materials. You can tune the band gap. You can emit in blue and green, which is very difficult to achieve in other conventional semiconductor. And that is the white LED that has been made possible by the blue LEDs and converting it by phosphor coating. Green LED and green laser diodes are also very active areas of research. And then I finally told you about transistors, high electron mobility transistors based on gallium nitride. If you recall, we do not have to dope these materials. The inbuilt polarization in the materials assists in generating the very high density of electron gas that can be used for a lot of applications like high speed RF as well as power electronics. So, those are some basic familiarities or basic awareness we should have about 3 nitride semiconductors, because these are a very big chunk of compound semiconductor industry now. So, today we shall start with the optoelectronic devices. So, we have a few lectures lined up. Today we shall start with solar cell, and maybe in a couple of lectures we will finish solar cells and photodetectors, and then another couple of lectures on LEDs. Okay. So, those will be essentially towards the end of this course now. So, we will come to the whiteboard. So, I will introduce with solar cell today. You already know how solar cells work, and irrespective of whether these optoelectronic devices are a part of your different entrance exam like NET, GATE or other things, it is important that you should be basic, you should have the basic knowledge and awareness about the design, about the types of working of these optoelectronic devices. So, solar cells are everywhere now. The power industry is heavily dependent on solar cell. There are many kinds of solar cell, many types of solar cell. Of course, there is organic solar cells. Those are used for flexible sort of displays and other things. You might use organic solar cell. You have conventional crystalline silicon solar cell, right? Silicon can be used as a solar cell, and crystalline silicon solar cell, and then there could be amorphous silicon solar cell, right? It's called asilicon. These will be cheaper, but of course as not as high performance as crystalline silicon solar cells. There could be multi-junction solar cell based on gallium arsenide, indium gallium arsenide and so on, right? Heterojunctions are also there, solar cells. There are also solar cells on other materials that are not exactly silicon or this compound semiconductor. There could be other materials that might be used, and one area is perovskite solar cell, which is very upcoming. These are perovskite oxides solar cell. Essentially in a solar cell you have the sun, no? You have the sun. So, sunlight should fall on some area, some device. Okay, sunlight should fall, and what you should get is that you should be able to get, if you connect a load, you should be able to get current. You shine light, you expose it to sunlight, and you should be able to get current. That is the basic photovoltaic action. It's called photovoltaic action, and this photovoltaic action results in this solar cell behavior. You are shining light and you are getting electricity out of it. That electricity can be used to drive your TV or charge up your phones and whatever, light bulbs and all. So, solar cell is a source of power. It is like a battery almost, you can say, in that it supplies electricity, except that you cannot store energy per se. It is a source of energy, but the sun has to be shining. If the sun doesn't shine, then you cannot get electricity or light. You have to store the energy separately in a battery. That is a different thing. But solar cell behaves like a battery in the sense that it gives you electricity without any bias voltage. You don't have to apply any voltage. Of course, you don't have to apply any voltage, right? Because if you apply voltage and get electricity, then how is it a solar cell? Then it defeats the purpose of being a battery or being a source of energy. So, you probably know that in India the government is also investing a lot and having many of the solar plants, and solar cell is becoming a very big thing now. Soon we will be moving to solar energy that will give us electricity in our houses. It's already giving, by the way, not at the whole scale of the country, but it will give. So, dominantly we get electricity from the hydroelectric power plants, the coal, thermal primarily, coal based energy, but those are fossil fuels that lead to depletion of resources, as well as those are non-renewable energy that gives you also a lot of carbon dioxide emission, a lot of pollution, a lot of issues. So, this solar energy is green energy. It is a renewable energy, because in the sense that solar energy doesn't die out, right? It's like an infinite source of energy. It's again it doesn't lead to pollution like carbon dioxide, emission and other things when you burn coal or petrol or other things. So it's a very awesome form of energy, except that it was a little costly, but now the costs are coming down. In many countries like Germany and European countries, you can see that solar cell is a big industry. India will also become a very big solar cell user. Already there are solar cell plants in the country, and they provide electricity to many areas of the country. By the way, I forgot the number exactly. Right. So solar cell is, in another 5 or 10 years you will see that more and more houses, industries, buildings, classrooms, everything will be lit by solar energy, electricity. You get electricity out of the solar energy. Okay. So that much So if you have done a course on semiconductor, if you are doing this course on semiconductor devices here in NPTEL, you should be aware of how solar cell basically works. Okay, you don't have to understand all this type of solar cell working, but basic solar cell is a PN junction, and a PN junction working very well, but there are certain aspects related to a PN junction which are used in solar cell that you should be aware of, and some figures of merit. How do you qualify a solar cell? How do you compare a solar cell? The very basics you should know, so that if someone asks you, you should be able to tell. Okay, that is what the motto is. So sun's energy, of course, is very vast, and solar cell is not only about a PN junction, but also about the energy that the sun gives us, right? So I'm not able to recall the exact number, but the solar energy is so much solar energy falls on the sun, earth, that if you have the earth here and the sun is shining here, if you are able to take all the energy that falls on the earth, all the sunlight that falls on the earth, if you are able to take all this energy, whatever energy is there, and you convert everything into electricity, then, or not even electricity, energy, then you should be able to meet 100% of the energy requirement of the world in a year. The 100% of the energy required by the whole world in a year can be harnessed by just, I think it is 1 hour of sunlight, or 1 day of sunlight, 1 hour probably. Okay, in 1 hour of sunlight, if the whole world's energy that it falls on the world can be captured, then you can generate electricity or energy that will cater to almost the whole of civilization. But the problem is, we cannot put a blanket of solar cell around the earth, so we only capture a very small fraction, and the efficiency also is very low. Very small area of the earth is covered. Okay, very small area of the earth is covered, and there are calculations to show that I think 16 kilometer by 16 kilometer area, if you have of solar panel in India, you can cover probably, I think, yearly electricity needs of the country. The solar energy is so much. Okay, solar energy is so much. So that's great energy. So it's a large amount of energy that we have to harness, and solar cell is basically the device that converts this sunlight to your electricity. Okay, so before we come to the working of how PN junction works as a solar cell, you of course know that when you shine light, you will generate carriers and you will get electricity. But let's have some basic ideas about solar energy. For example, what is the solar energy that falls on the earth? So in that context, there is something called air mass illumination. Okay, air mass illumination. What is air mass illumination? It is sort of a spectra of sunlight that you use in different conventions. It's called AM. So I'll tell you, suppose this is your earth. Okay, this is your earth, and of course you have an atmosphere. Atmosphere is almost same thickness, you assume. And suppose now you have a sun here overhead in the noon time. This is a sun. So when it comes directly like this, okay, on the surface of the earth, it has to cover some distance in the atmosphere. No, you take this distance as suppose L naught. Okay, L naught. So this is noon. Okay, and at suppose in the afternoon, 3 p.m. or 4 p.m., the sun will come like this, right? Sun will come like that, sunlight will come like that. So this path length that this travels in the atmosphere has now increased to L1. So this L0 by L1 ratio, that is the air mass illumination you tell. Matlab, what is the path length through the atmosphere the sunlight has to travel compared to the path length at noon time, because at noon time the path length is the minimum, right? So for example, if at evening the path length it is traveling is 1.5 times the path length at noon, then you call this 1.5. So the solar spectra in the evening will be called AM 1.5, air mass illumination 1.5. At noon, because it is 1 only, 1:1, at noon you will call it air mass 1. Of course, this exact nature of the spectra, although it is very similar everywhere, there might be differences depending on the local climatic conditions, clouds, covers and all other things, right. So, at almost very at near to sunset, you will have larger path length. So, you will call it AM something like 2 or something, and then your intensity will also come down and so on. Above the atmosphere, if you are here, if you are above the atmosphere like a satellite above the atmosphere, the sunlight will come directly without any atmospheric interference, and then you call it AM 0, air mass illumination 0. What does this actually physically mean? This air mass will actually mean the spectra. I will tell you what. Okay. So, essentially the sunlight is a black body, right. It is a black body radiation. The black body is at a temperature of approximately 5800 Kelvin. Okay. So, if you plot, this is the energy of the sun that emits as you receive on the earth, and this is your wavelength. You can say wavelength in micron, okay, or nanometer, whatever you say. Okay. So, this is energy. What is the unit? It is actually power kilowatt per meter square. So, every 1 meter by 1 meter area, how much energy you receive per nanometer of wavelength of light, because it is the density, spectral density. So, you see it will basically have a plot like this, it is a black body, right. So, it will fall like this. Okay. It will come down very, sorry, I am not drawing it very well. So, it will come like this. Okay. The spectral, the power, this is the energy of the sun per unit area per unit wavelength, and this will be around 500 nanometer of wavelength. The peak will come, this is lambda, I am telling nanometer, and I think here around around 300 nanometer or below, the sunlight is almost nothing, there is nothing. Okay. At around 300 nanometer it will come up rise. Then of course, this will be around 2 micron or 2000 nanometer, which is IR. So, it also has some wavelengths in the IR. Your human eye is visible in this range, around 365, sorry, around 365 nanometer to around 750 nanometer. Your human eye is sensitive. This is the sensitive area of the human eye, but sunlight emits slightly below the human visibility, that is UV, and also sunlight has a quite a large, not quite large, but there is also a important fraction of energy beyond the infrared. Okay. That is the thing. So, this is sunlight's energy, and this is the perfect black body. For example, this is a perfect black body. You can Google search, of course, black body radiation of sun. This is a perfect black body, and this is outside the atmosphere. I can call it AM. This spectra will be called AM 0. That means air mass illumination 0, which means I do not have atmospheric interference. So, I am measuring this outside the atmosphere, but the moment I come to atmosphere, what will happen? Moment I come below, come inside the atmosphere on the surface of the earth where we live, there suppose I talk about noon. So, AM 1 or AM 1.5 will be in the afternoon or evening. What will happen in that case? What will happen in that case is that let me erase this, excuse me, let me erase this part. So, what will happen is that when you come below the atmosphere, when you are living there, then of course, this intensity will fall down. This intensity will fall down because the atmosphere has absorbed, and also there will be some peaks that you will see like this. I am not drawing the exact location of the peaks, but you will be able to see some peaks like that. Some peaks will come here. Okay. Some dips will come in some wavelengths. Some wavelengths the sunlight will have some lambda, energy will be almost 0. Okay. Energy will dip. In the black body there is no dip, but in after atmosphere there will be some dips and peaks here. Those correspond to absorption. Those correspond to absorption of the sunlight by certain things like water vapor in the atmosphere. In the atmosphere, water vapor will absorb something. There might be absorptions from oxygen, absorbs from some nitrogen, and so on and so forth, right. There are gases there that will absorb. So, all these absorptions happen in water in the atmosphere, and fixed at the fixed wavelengths this water vapor or oxygen will absorb, and so in those fixed wavelengths there will be some dip. Okay. So, the black body pattern is still followed loosely, but the intensity has come down. Okay, and you will have some dips and peaks because those are the wavelengths at which the atmosphere will absorb the sunlight, that is why you do not reach them. Okay. So, that is, for example, this will be now AM 1 or AM 1.5. AM 1.5 will be even lower, probably slightly lower in magnitude, because your sunlight has to travel a longer distance in the evening, intensity will come down, noon intensity will be high. So, AM 1 will be higher, but AM 0 will be the highest because it is outside the atmosphere. So, this is what is meant by air mass illumination thing. Okay. And what is the y axis here? This is energy. I told you what are the typical values. So, the peak value is typically around 2. So, 2 kilowatt per meter square per nanometer. then 1, 0.5 and so on, right. So this 2 kilowatt at the peak you probably get around 2 kilowatt meter square per nanometer. Of course, if you integrate the whole area, under this, you will get this nanometer will go away because you are integrating with respect to this wavelength. So essentially you will get the energy in kilowatt per meter square. Okay. Of course, it depends on the area. If you have a 1 by 1 centimeter or a 1 by 1 meter area, your electricity will be, your energy will be more. The more the area, energy will be more. So anyways, the peak intensity is around 2 kilowatt per meter square per nanometer. Okay. This is your sunlight spectra and this is what you harness. Now the question is, semiconductors are used for harnessing this energy, for absorbing this energy and converting it into electricity. That is what we have to do. So now a simple question is, you might think about it, maybe we can answer it at the end. I will keep drawing this now and then. Okay. So this is the solar mass spectra, solar spectra in nanometer. So I told you that this is kilowatt per meter square per nanometer, and I told you that this will go something like this. So here maybe around 2 micron, the peak will be around 500 nanometer, slightly to the right maybe 510 nanometer or so. This will be around 300 nanometer and so on. So the thing is, a semiconductor, whatever semiconductor you use, and of course predominantly we use silicon because silicon is very cheap. Silicon is integrable to all CMOS, all electronics is silicon based mostly. So if you make something in silicon, it is easy to integrate, easy to scale up, easy to commercialize in a large scale. If you make a very exotic perovskite solar cell and all, then the large scale manufacturability, integration into the industry and all these things become tricky. So there is always a cost aspect. There is always a cost aspect, and silicon always wins in the cost aspect. So silicon, if silicon works as a solar cell, we will use silicon. Of course silicon works as a solar cell, and the good thing is that silicon actually works as a very good solar cell. You will see that silicon's efficiency can be very high compared to it can be almost it's not bad actually, it's very high. You will see that. I will not tell the number right now, but so silicon will be predominantly used as a solar cell, but crystalline silicon, that I am talking about crystalline silicon, like where you have band gap, where you have this crystalline, you grow it by Czochralski method or so. The crystalline silicon solar cells will have slightly better efficiency, but it's a little bit costly. I mean, it's cheap, but it's little costly compared to amorphous silicon that I call A silicon. Amorphous silicon is that is non-crystalline silicon, is amorphous. It's cheaper and wide scale you can use, although your efficiency will be little low. Okay, we will tell these efficiency numbers subsequently. Right now we are just introducing these things. So silicon is widely used. Of course, different applications, you can also use organic solar cells and different other kinds of solar cells that are used. Okay, but silicon is also very widely used, and silicon solar cells are extremely common. So you will use a semiconductor eventually as a solar cell, and semiconductor has a band gap. If you recall, you have a conduction band, you have a valence band. Okay, and suppose this energy is Eg. The wavelength of light that will be absorbed is hc by Eg. This is the wavelength of light that will be absorbed, and a photon whose energy is more than this also will be absorbed, but may not be very efficient in giving the electricity out of that. The most the most sensitive photons will be the ones that are corresponding to band edge, but the photons that are absorbed above this also will be absorbed, and they may not necessarily give you electricity, by the way, because these photons are absorbed to higher energies. So these electron hole pairs that are generated, they might thermalize and may not give you. Those things will come. Okay, and photons whose energy is lower than this band gap, which means suppose this band gap is, suppose I am telling you 1 micron, and the lambda corresponding to the band gap is suppose 1 electron volt, which is close to silicon band gap. The lambda corresponding to that will be around 1.2 micron. Okay, 1.2 micron. So essentially all the energy, photon energy whose energy is more than 1 electron volt will be absorbed. In other words, all the photons whose wavelength is lower than 1.2 micron, okay, suppose this is 1.2 micron. So all the photons of wavelength less than 1.2 micron will be actually absorbed in the solar cell, Okay, so it means the energy is higher than 1 electron volt. Which is the same as saying the wavelength is lower than 1.2 micron will be absorbed, and most of these could contribute to electricity. May not, all of them may not contribute, but most of them will contribute to electricity, which means all the wavelengths or all the photons of sunlight whose wavelength is more than 1.2 micron or energy is less than 1 electron volt, which is this will not be absorbed. So, those part is wasted, okay, those are of useless. So, for example, if I use a material of band gap around 2.4 or 2.5 eV for example, or 2.6 eV, which is very large, then you will have a wavelength of around 500 nanometer, which means it is the peak here. I understand this is the peak here, but the problem is that I can only absorb this. All the photons that have this energy will be absorbed and contribute to electricity. The rest, this part is actually wasted, because these are not even absorbed in the material. So, those are wasted. So, what does it mean? It means that to harness more and more of sun's energy, I need a semiconductor such that I need a semiconductor which can absorb everything, right? I need a semiconductor which can absorb everything from 300 nanometer to right up to 2 micron. What does it mean? That means I need a semiconductor whose wavelength will correspond to around 2 micron, or in other words, the band gap has to be very small. It will be hc by 2 micron, and that will correspond to very small band gap. It will be like 1242 by 2000, so around 0.6 eV, which means if I use a semiconductor with a band gap of 0.6 eV, which is much lower than silicon, maybe germanium or even lower than germanium. If I use a semiconductor of energy band gap 0.6 eV, then that will correspond to here, right? That will correspond to here, which means it will absorb everything. Here. So, that should be the best to harness the solar energy, right? But actually it is wrong. It is wrong because there are two things that will come subsequently in this chapter. It is not only necessary that you absorb everything that is there in the solar spectra, then you can use a small band gap material, but there is something called open circuit voltage. We will come to that. So, it is not very it seems obvious that if I use a very narrow band gap semiconductor, I will be able to get all the sun spectra will be absorbed, but the problem is there is something called open circuit voltage, and that open circuit voltage is you can say that it's a measure of how much voltage you can drop across your load when you are using a solar cell, and you want that voltage to drop is large, okay, then only you will be able to draw higher power and get better efficiency. If you use a narrow band gap semiconductor, your open circuit voltage actually suffers, so your efficiency comes down. There is some very beautiful trade off, okay, it's called Shockley-Quasar limit, okay, Shockley-Quasar limit, and that's something we have to discuss in one of these lectures now. You cannot arbitrarily have a small band gap material, it will not lead to an efficient solar cell, that is what is meant, okay. So, those are design things, we will come to that, okay. Now, but the basic thing is that you want to harness the solar energy that is there, you want semiconductor, and semiconductors have band gap. So, band gap means that you can only absorb light of a particular wavelength or wavelength lower than that, you cannot absorb wavelength light more than that, okay. So, this is the basic idea of a solar cell, and you might now want to take an example of a silicon p-n junction which behaves like a solar cell. So, suppose you have a p and n, and this is a wafer. Practically you will have a wafer like this, okay. You will have a wafer like that you make the devices, right. You make the devices. This is the z direction. Sunlight will come from here. But silicon is this is sunlight will come from here. A silicon p-n junction will have a depletion region that I define as this. This is your depletion region. Remember, if I draw the band diagram, it will look like this, right. This is your depletion region, if you recall, that is your depletion region, and that is this depletion region. Photons absorbed only in the depletion region will contribute to electricity, by the way, okay. Please remember, photons absorbed only in the depletion region will give you electricity. So, this is your Fermi level, okay. So, any photon that falls any photon that falls in the depletion region, it is absorbed here, no? That energy will be used to excite an electron from the valence band. An electron will be excited because that energy is absorbed sunlight. If the energy corresponds to the band gap or more, then an electron will be excited from here to the conduction band. What will remain here is a hole. So an electron hole pair is essentially created. Okay, I can say that an electron hole pair is created. There is a hole here, there is an electron here. Okay, so an electron hole pair is created for one photon if it is 100% efficient. Now when an electron is created, when a hole is created here, the default, even if you don't apply any bias, there is already a field in the depletion region. You know that because there is a slope in the conduction band, there is a slope in the valence band, so there is a field that you know. This field will push the electron in this direction because it will slide downwards. I told you, you think of it as like a floor and you think of it as like a cricket ball, it will slope downward this way. So electron will come that way. That field is sweeping the electron away without applying any voltage. This is default field, and this hole will be swept this way. So electron going this way means that current is going this way, and hole going this way means the current is going this way. Matlab both electron and hole current will be in this direction, and this direction is the direction opposite to the direction of a forward bias p-n junction current. In a forward bias, remember, this is n type, this is p type. So electrons are injected from this side, holes are injected from this side. So the net current flows in this direction in a forward bias. Remember, in a forward bias. But now the solar cell, when light is shining, the electron hole pairs that are generated are swept away in this direction, in this direction. So the total current because of solar cell is in this direction, which is opposite to the direction of the forward biased p-n junction. But of course you do not intentionally forward bias a solar cell. I am just leaving it unbiased, connected across a load. Maybe I will connect across a load. The load may be your table fan, your light, or whatever. Okay, so when you shine light, electricity will be generated in this direction. Okay, so current will flow in this direction. Okay, current will flow in this direction, and only this depletion region has the field. So your photons that are falling on the depletion region will only contribute to electricity. The photons that are falling here, the photons that are falling here will generate an electron here and a hole here, but there is no field. This part is quasi neutral. You remember, this is neutral. There is no field. So the electron that is generated here, the hole that is generated here, there is no field to sweep that away, and they will diffuse randomly and they will recombine. So the electron and hole produced in this neutral region is useless because they do not contribute to electricity. The electron and hole will diffuse and recombine within the p type layer, within the n type layer if the photon is absorbed here. Those are useless photons and useless electrons and holes that do not contribute to electricity, and that will contribute to reducing the efficiency of your solar cell. So you want the photons to be only predominantly absorbed in the depletion region, because only in the depletion region you have an electric field that can sweep the carriers away. Okay, so now if you come back to the structure, okay, so I will come back to the structure now. This is your P, this is your N, there is a depletion region here. Now your sun will be here, the photons are coming like this. These are photons that are coming, right? The photons will be absorbed in this neutral region, those are useless, and these photons that are absorbed will be so much that only very few photons will reach here, because the p layer will be thick, for example, and it will absorb all the photons. The fraction of this sunlight that is reaching the depletion will be narrow, very small, and your efficiency and working will be also terrible. What does it mean? It means that you do not want to waste the photons in the top p plus layer or in the top p layer. So you have to make this layer as thin as possible. You have to make the top layer as thin as possible so that sunlight is not wasted in getting absorbed there. Thin layer will absorb less, no, that is the funda. But if you make it very thin, there is a problem. You have to make a contact also. Remember, you have to make a p type and n type contact, a top contact, a bottom contact. If your layer is very thin, then your sheet resistance will be very large. Your sheet resistance will be very high, and that will be bad, because whatever, if you are trying to extract some voltage, a lot of this parasitic voltage will drop here. that will not deliver good power to the load. You do not want the sheet resistance to suffer. So, you have to dope it high. You have to dope the top layer high, very high. So, it is called P plus, the bottom will be N minus. So, first thing is that this layer will be thin, still this will be thin, so that sunlight is not wasted there. Still there will be a lot of absorption, still there will be very little absorption in this P plus layer, so that most of the photons are absorbed in the depletion. And secondly, it is doped high, so that the lateral resistance is not very bad, so that you can carry decent power, decent current and other things can flow. Okay. If your resistance is high, then current only cannot flow so much, I mean the voltage will be dropping unnecessarily. So, you want it to be highly doped and very thin, and when it is very highly doped and N is lightly doped, then most of the depletion will be on the N, and you want the depletion to be large, you want the depletion width to be large. Why? Because a larger depletion width will absorb more photons. A larger depletion width will absorb more photons, right. Suppose your depletion width is 1 micron in a PN junction, and another PN junction has a depletion width of 0.1 micron. Of course, there will be more photons absorbed in 1 micron than in 0.1 micron. That it means you will be able to get more electricity out. So, you want the depletion to be large. So, you want N minus, you want lightly doped N, and you want a highly doped P plus. But you will see that there are many design considerations that will ensure that you cannot dope this N very light also. Okay, you cannot dope this P very high also. There will be other problems that will come. So, what we will do is that we will wrap up the class here today. This is the first introduction to your solar cell. So, there are some design considerations I told you, in terms of PN junction and all the sunlight, the air mass, illumination, the amount of energy you can harness and so on. Next class we shall introduce some equations of PN junction and solve and try to express the expression for solar cell current, voltage, efficiency, fill factor. Those are very important. Once we do those, I will tell you about the practical considerations in designing a P plus N junction or an N plus P junction for a solar cell. Okay. And then I will talk about this efficiency and fill factor, which are very important, short circuit current and open circuit voltage, and we will try to see what is the Shockley quasar limit. You cannot arbitrarily have a material of low band gap to absorb all the light, it will lead to terrible efficiency. All those things we will discuss. Okay. And maybe we can have a quick introduction to other kinds of solar cell and other things. Okay. So, those we will take up in the next class. Thank you for your time.